In this video, I will be discussing the paper Addressing the Curse of Imbalanced Training Sets, One-Sided Selection. You can access a PDF version by clicking on the link in the description box. The general topic of this paper is learning from examples from the dataset. A typical scenario is where we have a training set. Each item here is called an example, from which a classifier is induced. This classifier is then assessed on an independent testing set. A complication arises when the training set is imbalanced, meaning a class is heavily underrepresented compared to the other classes. In this case, that underrepresented class is the oranges class. To make things even harder, there might be some data points that are hard to classify, or in other words, noisy, like an orange apple, for example. When assessing the classifier's performance, it might not do a good job classifying the examples. Yet, its average accuracy could be so high it makes it seem like the classifier is doing a great job. This problem is referred to as the curse of imbalanced training set. And in this paper, three main questions regarding this problem are being addressed. First, what are some existing ways to evaluate a classifier that was induced from an imbalanced training set, and how efficient those metrics are? Next, why does inducing a classifier from an imbalanced training set cause poor behavior? And finally, what is a better technique to create the training set when available data is imbalanced? To evaluate classifiers, measures are formulated from what we know as a confusion matrix. Some of those measures are accuracy, which is the percentage of examples correctly classified by the system. This measure is inappropriate when dealing with imbalanced training sets, as exhibited before. Other measures are precision, recall, and a combination of both into a more elaborate function called the F measure. However, in this paper, different set of measures were used to evaluate performance. These measures will evaluate the accuracy of classifying each class separately. That way, we can identify if the classifier is deliberately biased toward one class. Moreover, the geometric mean of those two measures is also a good way to measure the accuracy. This measure will only be maximized if the two accuracies are balanced. In other words, if A plus is high and A minus is low, the geometric mean G will be low, exhibiting the imbalance in accuracies. But why does an imbalanced training set hurt performance? In this paper, the nearest neighbor rule is used to classify examples, where classifying a specific item depends largely on its neighbors. To elaborate, let's take a look at this picture. We notice that because the number of apples is more than the number of oranges, oranges tend to have close apple neighbors, making it hard to draw the decision surface. As the number of apples increase, keeping a constant number of oranges, the noisiness of the domain grows. So does the likelihood that the nearest neighbor of any orange is an apple. This leads to many orange examples being misclassified. The paper also explains how using a Bayesian classifier or a decision tree for classification will also have a poor behavior in such circumstances. So, is there a better way to create the training set when available data is imbalanced? Well, there are several of those introduced throughout the literature. For example, duplicating the underrepresented training examples, or create new examples by corrupting existing ones with artificial noise. Other solutions are shown here as well. For this paper, an existing technique called tomic links was adapted to be used in better selecting training set examples when the data is imbalanced. That technique is referred to as one-sided sampling. So, what is one-sided sampling and how does it work? Before we get into that, I want to cover some of the concepts that will make understanding the algorithm easier. First, one-sided sampling is a technique used to select what examples should go in the training set. The main concept is to keep all minority examples, oranges in our example, even under the danger that some of them are noisy. They are too rare to be wasted. On the other hand, we will only select a representative subset of the majority examples, which are apples in this example. Second, there are 4 types of examples in a set. Those that are considered noise, like the apple in the bottom left corner, borderline examples that are close to the decision surface, those that are redundant, meaning they could be represented by other instances, and finally, safe examples, those that matter the most. Now back to the one-sided sampling. What are the types that can make it to the representative subset of the majority examples? Those would be the safe ones. Here I wanted to show what it looks like to remove the examples that do not make it to the training set. Figure 1 shows what happens to our example when all the borderline and noisy examples are removed. Figure 2 illustrates a further reduction where redundant examples are removed. If we use Figure 2 examples to induce a classifier using nearest neighbor or a decision tree, none of the problems discussed before should occur. It is time now to discuss the algorithm for one-sided selection. First, we start with the original imbalanced training set. Let's call it S. Next, a set C is created, including all minority class examples from S, and one randomly chosen majority class example. Using C as the training set, we classify S utilizing the nearest neighbor rule. We then move all misclassified examples from S to C, which makes C consistent with the original training set but excluding redundant examples. Finally, remove all majority class examples that are borderline or noisy, while retaining all minority examples. This resulting set is the new respectively balanced set. Now let's discuss the results of experiments using one-sided sampling and how effective that was. First, removing redundant majority class examples definitely help reduce the number of examples in the training set to a more balanced set. Nonetheless, it does not always guarantee performance gain. On the other hand, removing borderline and noisy examples balances the separate accuracy for both classes, in addition to improving the geometric mean. Moreover, when using one-sided sampling, raw accuracy can decrease. But as mentioned before, raw accuracy is not as an effective measure as the other measure mentioned. Finally, and as a rule of thumb, when wanting to use one-sided selection, first, look whether the value of A+ and A- are balanced. Only if one of them is prohibitively low, carry out one-sided sampling. Thank you all for watching.